We got a brand new broadhead from Wasp Archery to test. This is a traditional sharpshooter. They have their standard sharpshooter model, which weighs 100 grains. The difference here, this is a 150 grain broadhead. Now the market for the broadhead is really geared towards traditional archers. But I think as we go along here, you're going to see where it has pretty useful applications for regular, compound archers as well. I've been kind of a proponent for a couple years of shooting higher kinetic energy setups. Everybody's all obsessed with speed and wanting to get, the super high speeds out of their bows, and it's just caused all kinds of problems. The bows are louder. You're going to have probably more vibration hand shock. They're going to be harder to tune. I'd love to see that trend go away. I don't think a fast bow, aside from if you're hunting out west and you're shooting real long range, a super fast bow is not a help to you. It's a hindrance in a lot of ways. And I've been trying to tweak, the bows that I shoot and the arrow setups that I shoot a little bit differently to have higher mass weight, which equals higher kinetic energy, higher momentum, and it's also making the bow a lot quieter. So this is going to be a little bit of an abbreviated test because these are a prototype head. They're not going to change much, I don't think, but they're just not in production yet, so we only have a couple of them, so we can't do everything that we normally do, because if we break one, we only have like 1 or 2 backups to continue the test. So the first thing we're going to do is the most important test. We're going to see if these things fly accurately. Now my bow, it's December, I've been bow hunting, so it's set up to shoot a broadhead. So I'm going to shoot my field point, I'm going to shoot a drone broadhead just to make sure everything's still on, and then we're going to shoot this without changing anything and see where it hits. So that shot hit good. I aimed at that top dot because it's a little bit easier to pull out than in the center of that brand new target, and hit pretty much where I wanted. So now we're going to put this sharpshooter on here. Get these blades lined up with a fletch. Now, I might as well talk about the design real quick before I shoot it. So this is a cut-on contact head, and if you've shot any traditional archery, this is a very traditional style broadhead. It has a cutting tip. It's going to start cutting as soon as it enters, with a broad design. So you're going to have a lot of surface length. You're going to have, the blades are long, the taper is long, and it's going to end up with a 1-inch cut. And then it's got bleeder blades on the sides. Now you can shoot this without the bleeder blades. If you have a lower kinetic energy setup, like traditional archery, or a youth bow, or a lower poundage bow, taking those bleeder blades out will help increase penetration, and you're still going to get a good 1-inch cut. One of the things that you have with this style broadhead is sometimes you do have to figure out which way you want these blades to align with your fletch. Now I'm going to line them up so that the main blade is straight up and down with the cock feather on the arrow, and I may find that I want it differently, but we're going to shoot it that way this time, because I used to, it used to be back in the day, the only thing I hunted with was a recurve. So I've done a fair amount of messing around with traditional arrows and traditional broadheads, and that's how I know that sometimes the way you align this blade with your fletch can impact arrow flight. So next up is our tire. This is a steel belted radial tire. I don't know what it's off of. It's probably one of my cars from back in the day. But this is the ultimate penetration test. You have something that really simulates a deer's cavity, where you're going to hit some hide, which is the rubber, a little bit of resistance, which is the steel belts, which is a lot of resistance in this case, and that rubber has a lot of resistance to it too, because it's grabbing the broadheads that goes through. And then there's an empty pocket in the center of the tire, which is basically like a lungs, cavity in a deer. There's not any resistance there. And then you hit resistance on the other side. So a backstory on this is we've never had a broadhead completely blow through both sides of the tire. The Wasp drone has penetrated the best of any we've tested, and it goes completely through the front. It gets into the back side, and we've had the chisel point coming out of the back side of the tire. So in theory, with this extra 50 grains, I'm hitting a little bit more kinetic energy. This is roughly the same speed of bow that we've tested previously. This is a Matthews no cam HTR. It's shooting about 282 to 285 feet per second. So we're going to try to hit this thing square and see what it does. Alright, we got full penetration on the first layer. Just poked into the second layer, which is as good as any that we've done. I'll be honest, I was hoping to see it blow through the other side, because that would have really made my kinetic energy theory look pretty smart. But I might shoot this one more time once we go through the rest of the test, because I didn't quite square it up. I actually hit it a little bit of an angle on the tire, and maybe that impacted it. I don't think so, but I think it can go through both layers of these tires, and I want to see it do it. So when we get done here, I may shoot it again. But we're going to move on. We have 3 layers of plywood, and it's 3/8 inch plywood. And again, before in previous tests, we went through 2 of the layers and stuck into the 3rd, but we've never blown through all 3. So we're gonna try to do that. That is what I was hoping to see. We would have had complete full penetration through all 3, but we had to back it against this target, and this is a Reinhardt target. It's brand new, so you know that they're pretty stout, and it stopped it because I can almost push that through. The head is completely through. The most impressive thing that I'm seeing right now is this just went through those 3 layers of plywood, and this broadhead still looks brand new. And remember, it's not a chisel tip. This is just a regular cut on contact head. So the point of this broadhead, in theory, should be the weakest spot, because it's where the blades are .040 thick, which is a really thick broadhead blade. But if you compare it to a chisel point, that's not thick. No rolling, no bend, nothing, and it just blew through all 3 of these. That's what I was expecting this to do, to be honest with you. Alright, we're going to do one more shot here. We're going to shoot the concrete block. This is not a penetration test. This is solely to find out if the broadhead's going to break, where is it going to break at. So we expect something to fly. Well, that was fairly spectacular. We put our arrow into 3 pieces here. Actually, I guess 2. The knock just blew out the other end, but it absorbed the energy and ended up snapping that arrow shaft. And what we lost is the main blade, which again, this is cut on contact, so that main blade slides over to lock all of these parts into place, the bleeder blade and everything. And when that cut on contact hit that concrete, it actually made quite a large hole in the concrete, and then it blew. But what's impressive is everything besides that main blade here is structurally sound. So if you were to hit something that hard in the deer and it came apart, you still have a straight functioning broadhead. The ferrule is absolutely straight. I could reuse it actually. The bleeder blade, nothing got into it, so it wasn't damaged. Wants to come apart, these act like they're going to slide out just fine. And I could reassemble, that's crazy, I could reassemble this broadhead, put new blades in it after punching it into concrete, and reuse it. That's what, you know, a solid steel one-piece ferrule does for you, and it's what Wasp has shown us time and time again that they can do with their heads. They are extremely tough. So we were just kind of cleaning up our mess here, and we found the main blade. It's actually buried inside of that concrete. That's penetration. I mean, I said it wasn't a penetration test, but it penetrated into the concrete and it's stuck in there. So pretty impressed. So here's what we're going to do. We're done shooting it. We're going to head back to my office because I want to do some calculations with the kinetic energy just to illustrate the difference that this extra 50 grains is going to do. And we're also going to shoot one arrow through the chronograph to see how much it might slow down the arrow. Okay, so we got done with all of our penetration tests and stuff, and I wanted to see the difference between arrow speeds between this is a 100 grain Wasp drone and that 150 grain sharpshooter. And then what we're going to do is we're going to take those arrow speeds in to the office here, and we're going to calculate kinetic energy so you can see the difference that 50 grains makes. That was the 100 grain, and we're at 284.9, so we'll round it to 285. .267, we'll shoot one more time. 268. Alright, so we got our numbers. We're working with a 420 grain finished arrow with the Wasp drone, the 100 grain head, which would make 470 grains finished arrow with that traditional sharpshooter. So let's go ahead, I'm at the realtree.com kinetic energy calculator, so we're going to go with a 420 grain arrow, and we were shooting that at 285 feet per second. And that's giving us 75.74 foot-pounds of KE, kinetic energy, and 0.531 slugs of momentum. Okay? Let's go back up here. We're bumping this up to 470. And this went down to 268. And we got 74.94 foot-pounds of KE. Now here's where things get interesting. We got 559 slugs of momentum. So we lost less than 1 foot-pound of kinetic energy, but we gained 28 hundredths of momentum. That's where all this tweaking comes in. If we can figure out a way to add even 5 feet per second to that arrow speed and keep that same 150 grain head, look what happens. We're going to go up here to 273. I'm going to generate it. We've now at 77.77 foot-pounds of KE. We're up to 0.57 slugs. We are significantly increasing our momentum and our kinetic energy. So what could I do? Well, I could use maybe a slightly lighter arrow, and that might upset the balance a little bit, but I'm trying to gain some speed. Somewhere in the middle there is the maximum kinetic energy that I can get out of that bow. And you would think, well, you want to make that arrow lighter to increase the speed, but that's not going to do it because it's going to reduce your kinetic energy. Maybe you can add something to the string, those speed nubs that G5 has. Maybe you can get 2 or 3 feet per second out of that. Speed matters, but not at the expense of the arrow weight. That arrow is heavy, it's real quiet, the bow is real quiet, and I lost virtually nothing in kinetic energy, but I gained in downrange momentum, and it's momentum that's going to send that arrow through a deer. So don't discount those 150 grain heads. You know, we just showed in the testing that it's quiet, it's durable, it penetrates great, it flies great. I'm a big fan of using, you know, a heavier arrow, and that 150 grain traditional sharpshooter is certainly going to help put more punch at the end, and we're not even getting into the whole front and center conversation here.